Okay, so in this video we're going to go over how we know certain repeating decimals equal certain fractions. For example, you might reflect that you can actually show that 1 over 9 equals 0.1 repeating by using long division, right? You can take 1 divided by 9. How many times does 9 go into 1? Well, it doesn't, so we think of 1 as 10. 9 goes into 10 once. 9 times 1 is 9. Subtract the remainder, we get 1 again. Carry the 1 down here. 9 goes into this 10 once, right? 9 times 1 is 9. Subtract, we get 1 again. And carry the 0, right? And so forth. And we keep getting all these 1s, right? This hints at the fact that 1 divided by 9 is 0.1 repeating. So that's something we can do. But maybe you want to step back for a moment and think, were you able to show the reverse? If you start with 0.1 repeating, could you calculate or show that it equals 1/9? Could you prove it? Could you go in that direction? Or are you just memorizing a decimal to fraction conversion? And in general, how do we do this? Well, a nice approach, I think, is to use some basic algebra here. The typical approach to show that a repeating decimal equals a particular fraction is to start by setting the decimal that you're looking at equal to x. So this will always be referred to as x, right? And here we're eventually getting to that it equals 1/9. And of course, you know x equals itself. Don't get confused there. But we start by saying x equals our repeating decimal. So here, if I was proving this, I would say let x, right, equals 0.1 repeating. Now, in the case where the repeating pattern is 1 digit long, and it is here, it's 1, 1, 1, it's 1 digit, then we calculate 10x. Because when we calculate 10x, we move our decimal once to the right. And that's going to equal 1.1 repeating. And you can think about why this makes sense, right? If you take 0.1 repeating, it's really 0.1, 1, 1, 1, and so forth, and then multiply that by 10, what's going to happen to the decimal? Well, when you multiply a number by 10, the decimal moves once to the right. It becomes larger. But there are more ones to deal with. In fact, there are infinite ones. It's a repeating decimal. So really, when your decimal moves once to the right, you get 1 point, and then all the repeating ones after that. What does this allow us to do? Well, we can think about what 10x minus x would equal in terms of algebra and also in terms of the number values. So here 10x equals 1.1, so I'm going to rewrite this with its numbers, 1.1 repeating, and x equals 0.1 repeating. So all I did on the left hand side here was write 10x minus x. On the right hand side I wrote that in with numbers. What is 10x minus x? Well, that's 9x. What is 1.1 repeating minus 0.1 repeating? Well, you can think of this as subtracting all the 0.1 repeating from the number. So we have 1 right over here, 0.1 repeating. If we were to subtract the 0.1 section, the repeating section, this whole section just goes away, and what's left is 1. So 9x equals 1.1 repeating minus 0.1. Well, 0.1 repeating, well, that's just 1. And how do we solve for x here? We divide both sides by 9. And then what do we get? Well, these cancel out, and x equals 1/9. Now, what we just did there might be a little subtle, right? It might not feel you accomplished anything, but here we did it. We showed that x also equals 1 over 9. So think about this now. If x equals 0.1 repeating over here, and x equals 1/9 as well, then we know 0.1 repeating also equals 1/9. We've shown that the 0.1 repeating decimal is 1/9. And you might write it this way. So x equals 0.1 repeating, right? And x equals 1/9. So the transitive property, right? If 1 over 9 and 0.1 repeating both equal x, then they both equal each other. So these two are now equal, right? And this proof can be adjusted. Here we multiplied x by 10 because we had a 1-digit repeating sequence. Well, what if we gave you, I don't know, 0.23 repeating, right? So here in the 2 and the 3 are repeating. Well, what fraction does this equal, right? So what fraction does this equal? And how can we prove it? Well, let's re-examine our approach. So here, x is going to equal our decimal, equals 0.23 repeating. Now this time we're going to multiply by 100 because our repeating pattern is 2 digits long, and that'll really help us. So here, multiplying this by 100, it moves over twice. We have 23, and remember there are more 2 3's repeating after that. And now our proof would just show almost the exact same structure. We have 100x minus x equals the same thing over here in number form, 23.23 repeating, minus 0.23 repeating. So, think of 100x minus x. What's that in terms of algebra? That's 99x, right? And what's 23.23 repeating minus 0.23 repeating? Well, when you subtract the 0.23 repeating, that whole repeating section disappears. And all that's left is the 23, the whole numbers section. We want to know what x equals, divide by 99. And these 99's cancel out, and then we have our answer. X equals 23 over 99. And I encourage you to enter this into a calculator. It's nice to see that it works, right? 23 over 99, divide it, and you will get this decimal. It's true, these are equivalent. So here we start with x equals 0.23 repeating, and finish that it equals 23 over 99, and therefore that fraction decimal are equivalent. And let's try one more basic example, then we'll try a trickier one. So let's say x equals 0.12, I don't know, 4 repeating. So here, because there are 3 digits, we want to multiply by 1000x. And what that'll give us is 124.124 repeating. Multiplying by 10 moves our decimal once to the right, by 100 twice, and by 1000 3 times to the right. So if we have 3 repeating decimals, we want to move with 3 repeating digits, we want to move our decimal 3 times to the right. And why is that? Well, again, why do we want to actually multiply by why do we want to multiply so our decimal moves past the repeating sequence? Well, when we set up these equations, here we'll set up 1000x minus x, and that equals 124.124 repeating minus 0.124 repeating. Look how nice this is. Because we multiplied by 1000 and moved our decimal 3 times to the right, we're able to cancel out the repeating sequence here, right? We subtract 0.124 repeating, and that lines up perfectly with what's left over in the first decimal. So we have 124, right? And that will always work. And here on the right we have 999x. To solve for x, we divide by 999. Cancel out here. And then we have our fraction equivalent, where x equals 124 over 999. And all we did was show that that is the correct fraction for this decimal, that they're equivalent. Now, in other cases, right, you might have there are all kinds of variations of repeating decimals. These are probably the ones you will deal with directly in most typical classes. But if we switch things up, we can really have some fun with these kind of proofs. For example, what if x, right, was 0.02 repeating? Well, here now, because the 2 is repeating only, that is different, by the way, we'll show this as well, as 0.02 repeating. These are not equal to each other, right? If we think about this on the right, we have x equals 0.020202, and so forth, because the 0 and the 2 are repeating. But on the left here, x is going to be equal to 0.022222, right? So these are clearly not the same thing, so how do we deal with them? Well, on the right here, with 0.02 repeating, we would set x equal to 0.02, our decimal, and multiply by 100, as we've been doing, right? So here we move our decimal twice to the right, and we get 2.02 repeating. And our proof is basically the same as before. 100x minus x equals 2.02 repeating minus 0.02 repeating. In algebra, 100x minus x is 99 groups of x. And over here, take away the 0.02 repeating from 2.02 repeating and just get 2. We finish by dividing by 99, right? And then we get our fraction. X equals 2 over 99, right? Okay, so those are equal. But what will happen here in this more interesting example? What do we want to multiply by? Well, here, right, our pattern begins in the hundredths place. Um, so there are ways to deal with this in terms of breaking it apart. We can think of this as 10 times smaller than 0.2 repeating. So for example, if y equals 0.2 repeating, and we know that gives us 2/9, then I know x, which equals 0.02 repeating, that's just 10 times smaller. This decimal has moved over one place and made it 10 times smaller. We give us 2/90, which is 10 times smaller than 2/9, and that's the appropriate fraction. But how do we prove this with this algebraic approach? Well, here what I would do is I would say let x equal our decimal, as we've been doing, 0.02 repeating. And here I would find 100x, right? And 100x is what? Well, it would be 2, and then you have 0.02 repeating after that. Or do we, right? Think about this for a moment. What just happened? That's not actually true, right? This is where things change now. If we look at, let me rewrite this decimal right here. This is 0.02222 and so forth, right? So here, when you multiply by 100, your decimal moves twice to the right. So think about this carefully. 100x would then equal 2 point, see, it moves once, twice, and then 2 repeating. So here we can't just subtract x from it. If you subtract 0.02 repeating, it won't cancel out with this 0.2 repeating. So what we need to then do is find 10x. And 10x equals what? Move once to the right, and 10x equals 0.2 repeating. So this is a little bit trickier because you need to plan out what you multiply by so that the proof will actually cancel out the terms, the repeating decimal portion, and then work. So here we have 100x's minus x, and that equals 2.2 repeating minus 0.2 repeating. So see, I knew I had a 0.2 repeating here. So strategically, I need to then pick a second term that when I subtract it will cancel out the 0.2 repeating. So I found that by multiplying this by 10. So here 100x minus x is, minus 10x, right? We found 10x here. So 100x is minus 10x, that's 90x. And 2.2 repeating minus 0.2 repeating is just 2. Solve for x by dividing by 90. And then there we have it, x equals 2/90. And that's I think is complicated of an example, or at least I should say that starts to get into the interesting world of complex examples with these proofs. All right, thanks a lot.